Okay, maybe we can start. Last time, it was some time back, so it's been now a couple of weeks. So let me just remind you, where we stopped. Yeah. So where we stopped last time was we looked at the interaction picture, and remember we were looking at this equation. We are trying to look at the evolution of this operator, and this operator had some evolution of this kind. And remember, we found this answer which looked like and then so on, right? And we wrote this whole thing in this form as sum of minus I to the n, then factorial time order product. This is sometimes written as the time ordered product and what this means is that you expand out the exponential and apply the time ordering to every term. Okay, and this interaction picture operator is very important because this interaction picture operator tells us how to go from the interaction picture fields that we can calculate basically using free field evolution to the Heisenberg picture fields, which are the ones that we want. See? Once we have in hand the Heisenberg picture fields, then we know everything about the theory. Okay? Then we can just insert the Heisenberg picture fields and we'll get the answers that we need. Okay. So this is called Dyson's formula. This is the one that we derived last time. Are there any questions about this and how we derive this? Do you remember this, or do you want me to remind you a little bit more about how we got this? This is all in your notes, right? This is where we stopped last time. Okay, fine. Now the main thing that we want to do is, maybe one more thing I said last time. Let me just remind you. Let me remind you, these interaction picture Hamiltonians in the end had some simple expressions in terms of the interaction picture fields. So for instance, if you take a lambda phi to the 4 theory, you take the Lagrangian to be this is an example of an interaction picture Lagrangian. You can write down something else, okay? Then this thing hi of t looks like lambda phi I of xt to the 4 by 4 factorial, okay, and d3x. Once you put the integral of time, it will become a d4x, but this interaction picture Hamiltonian, is just an integral of d3x. But the important part is that it looks like, the interaction picture fields at that time raised to the power 4. So what appears in the interaction picture Hamiltonian are not the Heisenberg fields. Okay? If you write down the full Hamiltonian corresponding to this, then the full Hamiltonian corresponding to this will have Heisenberg operators here. Okay? It doesn't have interaction picture operators, but this interaction picture Hamiltonian, remember, it's not just the difference of what you might call, it's the difference of, right. So, it's not just at an arbitrary time t, it's not just the nonlinear part of the full interaction, the full Hamiltonian. Okay? That full Hamiltonian would have here Heisenberg picture operators, but what appears in the interaction picture Hamiltonian here are these interaction picture operators. Okay? That's because you make some split between the interacting picture and the Heisenberg picture at some point of time, and then the interaction picture Hamiltonian is obtained by evolving that part, okay, using the free Hamiltonian. That's why you get this here. Okay, this I also explained. Okay, okay, good. Is this clear? Yeah. Okay. So this is where we were last time, and now I want to say a little bit about what we want to do with this formula, right? So what do we want to do with this formula? So eventually, what we want to compute as I said, eventually what we want to compute is how some in states go to some out states, okay? Or in general, what we might want to compute is how, what the matrix elements of this unitary evolution operator would be, okay? So the most that tells us that what we want to compute are expectation values of these kinds of products, okay? So what we want to compute are maybe or matrix elements. Okay, yes, our matrix elements are these guys. So this is the main object that we want to compute in perturbation theory. Okay, why? Because once we can compute the matrix elements of this object, then we can compute, we can sum them up and we can compute the matrix elements of that time of interacting of that UI. And once we have UI, we know everything about the theory. Right? So this is the main thing that we want to compute. As I just said, remember this interaction picture Hamiltonian looks like that, right? Something like that. So what we really want to compute, these are some integrals of some polynomials by this I mean polynomials in interaction picture fields. In the example that I wrote, these polynomials have a specific form. Okay, you get phi I to the power 4 at every point. But in general, you can think of that as a limit of polynomials. So you look at phi x1, phi x2. In general, what you have, so that's why I didn't write an equality here. What the point I want to make is that in general, what you want to compute in perturbation theory are expectation values of polynomials of products of, or expectation values of such products of interaction picture fields. There's some sums, so in general they're polynomials, but that is the basic object that we want to compute. Okay, is this clear? Yeah. Yeah, the psi1 and psi2 are the in and out states. In the end, it will turn out that we will often only be interested in vacuum expectation values. Just one second, let me just it'll turn out that in the end, once we get to the end of our formulation of quantum field theory and the S matrix, we will formulate this only in terms of vacuum expectation values. But for now, you're right, psi1 and psi2 could be will be the in and out states that we get. And when we first do perturbation theory, we'll do it lively, and we'll have non-trivial states. In the end, actually, we are going to formulate something, using what's called the LSZ prescription, where you only compute webs of these guys. But for now, we are being very general, and we are allowing these psi1, psi2 to be in some arbitrary states. Okay, is this clear? Okay, good. Let me remind you, what these interaction picture fields are. Okay? These interaction picture fields, remember, are which means you take what we call the Schrodinger operator, by which we mean the Heisenberg operator at some time 0. The fact that we chose time 0 is not important. Okay, you could have chosen some other time. We're just choosing time 0 for convenience. There's no meaning of time 0 in general. Okay, and you evolve it with the free Hamilton. Okay? But we know what this expression is as a function of time. Why do we know this? Because in the beginning, we spent a few lectures trying to solve the free field theory. Right? When we solved the free field theory, this is what we were doing, right? We were evolving things with the free field Hamiltonian. We were evolving the free field with the free field Hamiltonian. So we know what this is, and we know the expression for this. It's just our old expression, which is okay. Remember, these are 4 vectors. These are 4 dots, but the integral here is only over d3p. And there's some normalization we've been carrying about for a long time, which is the square root of twice omega p. Okay, is this clear? What we have here? Yeah. Yes, phi I satisfies the free Klein-Gordon equation. Exactly. Right? Okay, so we know what this is. So what do we have to do? We have to take this, we have to insert this, and we have to evaluate some time ordered products. And once we've evaluated some time ordered products, then we will have completed everything about QFT. Okay, so so that's the program. You take this and insert this into these time ordered products. Okay. Okay, good. Are there any questions about this program? Okay. However, when you just look at these time ordered products, it looks like it's a bit of a mess. It looks like it's a bit of a mess because what is a time ordered product, right? Time ordered product tells you put later on the left. So let's say we just set out to evaluate this time ordered product. What would we get? What we would get would be, one ordering. We get theta of x10 minus x20, theta of x20 minus x30, so on. Xn minus, this is one ordering into the vacuum expectation value of phi of x1, phi xn, plus other orderings. Okay, there could be another ordering where maybe x20 is larger than x10. Okay, and all the other theta functions are the same. Okay, I'm just trying to tell you how this is going to be a mess. You don't have to copy this down. I'm just trying to explain why it will be a mess. Yeah, and then you will get here phi I x2, phi I x1, and phi I xn. Okay, so you see plus other orderings, plus n factorial minus 2 orderings. Minus 2 because we wrote 2 explicitly. Okay, so there are many other orderings. So do you see when you look at this time ordered product, what will you get? You'll get various such combinations, right? Theta functions times a product, some other theta functions times a product, plus some other theta functions times a product. Now, in each of these products here, you will find that you have a product of lots of these guys, right? So each of these things also has 2 to the n terms in principle, right? So this has 2 to the n terms. You see why it has 2 to the n terms? Because each field has a creation annihilation operator. So there are 2 to the n terms, right? And then you have to commute various things and write down various delta functions, right? And you'll get a mess. In fact, this is so messy that even if you use the help of computers and you just try to evaluate this by brute force, you'll find there are way too many terms very fast. So this is the first point to realize, which is that we used Dyson's formula to reduce everything into evaluating the matrix elements of these kinds of products. But these kinds of products look like there are a lot of combinatoric terms here. Okay? And so it doesn't look like it's something which is very efficient to evaluate, and certainly not by hand, and maybe using computers, but even then by hand it looks very hard, and even using computers you'll find these expressions soon become very messy. Okay, so there's a very important tool that is used in quantum field theory to simplify these kinds of expectation values. Okay, and that's called Wick's theorem. is, simplifies okay, and that is going to turn out to be something which is very important. Okay? So you might say, well, there's nothing deep, you're just trying to simplify lots of terms, but these terms are very messy, and so this is an extremely important tool, okay, which tells you how you can write down how you can efficiently evaluate these kinds of products. Okay. Okay, so the main thing I want to do in today's lecture is explain Wick's theorem, okay, and tell you how you can use it to efficiently evaluate these kinds of matrix elements. Okay, do you see? Okay, is this clear? So where we are going, what the program is, where we are going. Okay, good. Let me now state the theorem, and then we'll prove it. Okay. Okay, good. Before we state the theorem, I should just remind you of normal ordering. Okay. Once before in this course, we encountered the concept of normal ordering, right? And the concept of normal ordering was that, so that's time ordering, and there's another kind of ordering that we encountered, which was normal ordering, which we defined for products of creation and annihilation operators, right? So we said AK1, AK2, AK3 dagger, AK4 dagger. If you had such products, normal order just means place all creation operators on left, and annihilation ops on right. Okay, do you remember this? Yeah, that's what normal ordering means. That's different from the ordering that we have above. Okay, that's time ordering. Now we can define a notion of normal ordering also to these kinds of products that we have of these interaction picture operators. Okay, so when I don't write T explicitly, it means we don't need to worry about I'm writing a 4 vector. Okay? If you see an expression, sometimes I'm writing xt there, and that's because we had an integral over t. Okay, here we don't. Then I wrote an expression phi xt there because again we had a t there. But in the end, that expression you can think of as a 4 vector x. Okay, so we are moving a little bit between 3 vectors and 4 vectors, but please be careful when you do this. X on. I'm not all. I should be careful to write vectors, but I'm not always doing it. Yeah. Okay. Good. So you see this kind of expression. Also, you can define a notion of normal ordering, which means expand in creation and annihilation operators and normal order, right? So it's the natural definition. There's nothing deep about this, right? You just take this, you expand this in terms of creation and annihilation operators, and then you put all annihilation operators to the right, all creation operators to the left. Okay? In fact, it's useful to think in terms of 2 different parts of the field. Okay? So another way to do this is to write phi I as phi I plus phi I minus as the positive frequency part and as the negative frequency part. And the positive frequency part is defined as, remember that you see there are 2 terms there, right? So you can write this as And the negative frequency part is the one that contains the creation operators. Okay, this is some convention. Actually, I have to say, I always kind of militate against the convention and tend to call sometimes the positive frequency part the one that contains the creation operators. But the standard convention is to call positive frequency the one that contains the annihilation operators, and negative frequency the one that contains the creation operators. Okay, but these are just names. You can choose what you want to call positive and negative. Okay? But there are two parts. Okay? And this one is, following standard convention, we'll call this the plus part and we'll call this the minus part. And it's just obvious that phi I is the sum of the phi I plus and the phi I minus parts, right? Okay. So what does normal ordering mean? So I can also say it this way. Right? Instead of saying expanding in creation annihilation operators, I could write each of them as positive and negative frequency, and I could put all the positive frequency parts to the right. Okay? Notice that when you expand this, you will get a lot of terms. Okay? So, for instance, let's say I compute phi I x1, phi I x2, right? Let me just tell you how this makes a difference. Okay? So, if you just computed the product, what would it look like? There would be 4 terms. Okay, the plus plus, plus minus, minus plus and minus minus terms. Okay, if I computed the normal ordered product, then these terms don't get affected. This term does get affected. Okay, this term does not get affected. And this term does not get affected. So only one term changed. So you see the difference between normal ordered product and the full product here was that only one term changed. In general, if you had more terms in the propagate inside the normal ordering, more terms would change. Okay, but do you understand then how the normal ordered product works? Okay, good. Okay, and we are still trying to get to Wick's theorem, but I'm just trying to introduce some terminology. Okay, okay. Now we have two kinds of products. We have the time ordered product, which we discussed earlier, and we have the normal ordered product. Okay, we are going to define a third thing, which is the contraction. Which is the difference of the two kinds of products. Notice, by the way, normal ordering is only defined when you have interaction picture operators. Okay? If I tell you, compute the normal ordered product of several Heisenberg picture operators, that doesn't make any sense. Okay? Because Heisenberg picture operators have all sorts of things, have creation, annihilation operators. So normal ordering is well defined only when you have these interaction picture fields. Okay? When there's a clear separation into with creation and annihilation operators. Okay? Sorry, I want to define now the contraction. Okay? This is called the contraction, and it's denoted this way. And the contraction between two such fields, x1 and x2, is defined as the time ordered product minus the normal ordered product. Okay, so as I said, there are two different products that we have. We also have just the ordinary product, but that's not appearing here. The time ordered product means what? You take the full field, you put later on the left. The normal ordered product means what? You take the positive and negative frequency things and you put the positive frequencies in the right. Okay. The difference between these two kinds of products is called the contraction. Okay. Is this clear? Yeah. Okay, good. Now, this contraction is actually a number. Okay? The normal ordered product and the time ordered products are operators. Okay? They're both operators. However, this thing is not an operator, it's a number. Okay, let's see that. Where did I put that? How do we know that? Well, we can just calculate it explicitly, right? So remember, the time ordered product just looks like plus okay. Now notice that what I'm going to do is I'm going to take this and I'm going to subtract. So that's phi of x1, phi of x2. Okay. If you look at the difference of phi of x1 and phi of x2, remember I said only one term change, which was this term. Okay. So if you look at the normal ordered product also, of course, you can write as I can just introduce theta functions. What I'm writing right now is a trivial equation, but I'm just writing it to make this. This is a trivial equation. I just wrote one as theta of x1 minus x2 0 plus theta of x2 0 minus x1 0. Okay, but it's helpful because if I want to now compute the difference of these two guys, I have theta of x1 0 minus x2 0 and the difference of the ordinary product and normal ordered product. And here I have theta of x2 0 minus x1 0, and again the difference of the ordinary product minus the normal ordered product. You see, this difference we can already compute from the expressions that we have on top. Okay? If I compute the difference between the ordinary product and the normal ordered product, you see this term gives you 0. This term gives you a commutator between plus and minus. Okay? This term gives you a 0 because there's no difference. It's still minus plus. This term gives you a 0. Okay? So this gives you into phi I plus. So the contraction is equal to theta of x1 0 minus x2 0, the commutator plus, then you can see it's the other commutator. Okay. Do you see how this happens? You see what did I get from here? Let's say I subtract these two, right? It's only this term that changes, right? What is this term? This term is just the commutator of phi I plus with phi I minus. So phi I plus of x1 with phi I minus of x2, right? And that's this term. The other term you can just write down by symmetry, and it's the commutator of phi I plus of x2 with phi I minus of x1. You see that? These commutators, remember, are numbers, right? Because we had here the expression of phi I. This is phi I plus, this is phi I minus. Remember, phi I plus phi I minus is some delta of p minus p prime. Right? Sorry, AP dagger is just is just a delta function. Right? And therefore, when you take the commutator of phi I plus with phi I minus, it's the commutator of this part with this part, but there are no operators in there. They're only numbers. You see that? There are no operators left. So this is a number, and this is a number, okay? And the sum of two numbers is a number. Okay, so that's why the whole thing is a number. Okay. Okay, that's why this contraction is a C number. We'll compute it explicitly at the end of this lecture, but for now we just need to know it's a number. It's not an operator. Okay. Okay, is this clear so far? What we've done? Okay, now if we're in a position to state Wick's theorem. Okay. Let's go back on the top slide.
Excuse me, sir.
Yeah.
Why there is a need to define contraction in quantum theory?
Because we'll use it in Wick's theorem.
Okay, so to prove the Wick's theorem, we need the contraction.
Even to state the Wick's theorem, I have not stated it, but we even to state the Wick's theorem, we'll need a contraction. Yeah, whatever we are doing is for some reason. Yeah. Huh? No, they're not equal time commutators. The what? Where did we use the result of equal time commutators? AP dagger, there's no time in AP. AP dagger is just this. That doesn't have anything to do with equal time commutators. AP doesn't have a time. It's an operator. So what was our normalization? 2 pi cube. We've been using 2 pi cube, right? Okay. So this doesn't have anything to do with time. There's no time. It's just an operator. Okay. There's some equal time commutation relation has to do with phi I and pi I, okay, at the same time. But this doesn't have to do with any time. So all we used here was the fact that this commutator was a number. Okay. It'll have some various dependencies on time. Okay, good. Yeah. Yeah.
The next one we will take some q dot 1.
Yes.
So how we will accumulate those two terms to bring out that 88 time?
Whatever it is, it's a number, right? Let's compute it. We don't need to accumulate anything. I'll do this computation at the end, but notice that phi I plus, by the way, can you guys see if I write with the yellow chalk, it's a little better in terms of dust, maybe. You can see, right? And on the Zoom also you can see?
Yes.
Oh, fine. You see, phi I plus is some APs, right? So this looks like this is what you're saying, right? We'll compute this in a minute, but right now all we need to know is that this is a number, right? This is delta of P minus Q into whatever, right? Same measure. All we need to know is this is a number. What number it is, we can compute later. Is this clear? Yeah. So, sorry, who asked the question? You asked. Yeah. Huh? You asked the question. Sorry. Yeah. So this is. Do you see why it's a number?
Let's check
Yeah.
that when we will do the computer.
But what is there to check that it's a number? It's not an operator. There are no operators left.
I cannot means one of the AP AQ dagger will contain EX minus QY.
Okay, let it contain. So
And
here's
the
minus
other
IPA.
part of the computer will contain minus PX plus.
This is the full commutator. We already did the commutator. This is a number, right? That's all we want to check. Whether it's simple or not, or whatever it is, this will turn out to be simple also, but it's a number, right? That's all we want to, that's all we want to check. It's a number. It doesn't have any, there are no operators left here. You see that? So what's the confusion?
My confusion was that along with AP is coming a e to the power minus iota p dot x.
Yes.
Along with AQ dagger, it's coming e to the power plus iota p dot
Yes.
y. And the reverse thing will also be there in the commutator.
No, this is the commutator phi plus and phi minus. That's what we have here. We are not computing the commutator of phi I with itself, but yeah, let's say it was there then.
So then one of the terms will contain e to the power.
Okay, let it contain, but it's still a number, right? Whatever it contains, whether it has px or qy or whatever, these are all numbers. All I'm saying right now is it's a number. We'll compute what the number is in the end. We have to do some integrals. But you know, even before you do the integral, you just know the answer is a number. That's all I'm trying to say. That's all, right? So that there should be no confusion about. What the number is, we can evaluate it. But it's by number, I just mean there are no operators in it. Okay, good. So let's state Wick's theorem.
Excuse me, sir.
Ah.
We are always using commutators. Do we at any point use anti-commutators?
Do we at any time use the anti-commutators? Anti-commutators have not appeared here. We might use them at some point. You know, if you were to do the same thing for fermions and so on, you would see anti-commutators. But for bosons, there's no natural reason to consider anti-commutators. Anyway, what appeared here was a commutator just by difference. You know, it just by construction. I defined the contraction to be the difference of these two, and I found that it had a commutator because it was the difference. Right?
Yeah, right.
So I could have defined some sum or something, and maybe I'd have got anti-commutators, but we're not. That's not of any use for us. Yeah. Okay. Good. So let's state Wick's theorem. Yeah, we can state it here. Okay. So this is the following sum of normal ordered products. Okay. The fully normal ordered product okay plus I'm putting these contractions inside the normal ordering because it doesn't matter, they're numbers, right? okay, plus terms with two contractions. Like this one, okay, and so on. Plus, if I got the combinatrix right, half into n into n minus 1 by 2 minus 2 into n minus 3 by 2 terms. How many there are doesn't matter, but you know, with two contractions. Okay. Plus, and you keep going like this, e contraction terms. And at the end, you get, okay, so n terms with one field uncontracted. This happens only if n is odd. Okay. Otherwise, you get the all contractions. Yeah. Okay. Sorry, not n terms. Okay. If n is even. Okay, so this theorem looks a little complicated, but it's easier to state than it is to write. The theorem is just you write the time. You see, we define the contraction to be the difference of the time ordered product and the normal ordered product, right? For two fields. Now the theorem tells you that if you have a product of n fields, you can write that as a product of the full normal ordered product plus terms with one contraction, plus terms with two contractions, plus terms with three contractions, going all the way down, okay, till you have, if n is odd, you have one uncontracted term, which is the maximum number of possible contractions, or you know, if n is even, if you have all terms which are contracted. Okay. And here I happen to have contracted x1 with x2 and x3 with x4, but I emphasize that there is no reason I had to contract x1 with only x2. That's why there are many other terms that you get here. If you look at the set of terms with one contraction, there are n into n minus 1 terms. By two terms you can contract, because I could contract one with 2 or one with 3 or one with 4 or one with n, or maybe I could contract 2 with 3 or 2 with 4, right? So there are many terms. It's not that I have to contract 1 with 2. I just happen to have written that because that's the first term, right? And I can't write down all terms, but there are all possible combinations. Similarly, you know, here I chose to contract 1 with 2 and 3 with 4, but I could have chosen to contract 1 with 4, 2 with 3, or maybe 1 with 5 and 2 with 10. Okay. So there are many such combinations that you have. There are lots of combinatoric terms, but the basic thing is these are all terms with one contraction, all terms with two contractions, all terms with three, and so on. Okay, plus all terms with n contractions. Okay. So is the statement of the theorem clear? Okay. And everything is inside normal ordering at all steps. Yeah. There should be where? Yeah, there will be n by 2 contractions in the last part. That's why n has to be even. So if n is even, then there'll be n by 2 contractions. There are many possible ways of doing n by 2 contractions, of course. This is not one term. actually all terms fully contracted. Sorry, yeah, I should have written a plus dot dot dot. This is plus all terms. You know, it's not that, as I said, it's not that 1 with 2 and 3 with 4, right? I could have, if you want full contractions, then 1 will contract with 5, 2 will contract with 10, right? All possible ways of fully contracting.
First you contract and then normal order.
It doesn't matter because contractions are numbers, as we just discussed. So, you know, it doesn't matter. The fact this I put inside normal ordering, but it's kind of trivial because it's a number actually, and there's no normal ordering really. Yeah. Okay, is this clear? Okay, so this is the statement of X theorem. Huh? Yeah.
Is it the phi 1, x1 and phi 1, x2?
Yeah.
But ordering normal ordering doesn't apply to this.
This is a number, right? So this is a contracted, this is just a number. So there's no normal ordering here. This whole thing is a number of x1 and x2.
Normal ordering is on the rest of the.
That's correct. That's correct. Okay, is this clear? The statement of the theorem? Okay, let's prove it. Okay, good. Okay, good. So let's prove the theorem. We'll prove it by induction. Yeah. So for n equal to 1, there's no theorem, right? Because there's nothing to say. But for n equal to 2, this is just obviously true. This is equal to normal order term. Plus there is only one contraction. Which is the last term that we had here, and there is only one of them to choose. And this is just true by definition of the contraction, right? Yeah. Okay. So this is just true by definition of the contraction. Do you see? For n equal to 2, this is how we define the contraction to be the difference of these two. Okay. So Wick's theorem is obviously true for n equal to 2. Good. So say okay. Then we want to prove that this works for n going to n plus 1. Okay. Let's call this expression, whatever you get on the right hand side, let's call it W. There's just some name I'm introducing for this sum, so I don't have to keep writing this. Now for n equal to 1, let's assume okay, this is true without loss of generality, that x10 is the latest time. Why is this true without loss of generality? Because no one told us how to pick the names of the different variables, right? So I want to prove Wick's theorem for n equal to for n plus 1. Let me just call the latest time x1. Yeah? It's not like I have an expression here, and I've assumed that Wick's theorem is true for all n, right? So let me just say when I have n plus 1, that the term which has latest time, I'll call that x10. Okay? So there's no loss of generality here in assuming that x10 is the latest time. Okay, you see this? So x10 is yeah.
X1 to Xn comes as a right. They are actually 4 vectors. Right?
There are 4 vectors. Yes.
So for distinguishing any one of them from the other, any one component can be different, right? It happens that the time component is same and the components are different. The time ordered product would contain a whole square of that, right?
Why whole square?
Means the time ordering, how will you do the time ordering of both the operators at the same time? The different space points.
It doesn't matter in that case, whether you put one to the left or one to the right. It doesn't matter because operators at the same time commute, remember. Yeah? So it doesn't matter which, there's no ambiguity in time ordering. If the points are spatially separated. Okay, is that clear? Okay, so I'm just going to assume this is just a notational question. Let me call the latest time x1. Okay? Then you see that the time ordered product of phi I x1, phi I xn plus 1, right? This is what I need to evaluate. But because x1 is the latest time, this is just phi I of x1 times the time ordered product of phi I of x2 to phi I of xn plus 1. This I'm just saying, this in this thing, let me just call whatever latest time, let me call that x1, and then this is true, because then the latest time is to the left. And these I have to time order in whatever way I need to time order. Do you see that? Okay, good. But now we have an inductive argument. Right? What is the inductive argument? The inductive argument is we know that this is equal to the right hand side of Fick's theorem, which is W. Okay? So this is equal to, by the way, W, notice, is an operator. Okay, W is not a number. Do you see why did I write W? Somewhere I wrote W. Didn't I write W or did I erase it? This is, I wrote W, yeah. So this is W. Okay, this W is actually an operator, because what appears in the right hand side of Fick's theorem is an operator. You see that? It's not a number. Because that normal ordered product, for instance, in the first line is an operator. Okay. So okay, this is true by our inductive hypothesis, right? You see, so this is just true by inductive hypothesis, that we get some. Okay, good. Now that's too bad. Anyway, maybe let's work on this too. Okay, let's keep the theorem up and let's keep working on this board. Now, phi I of x1 looks like phi I plus and phi I minus, right? I didn't do anything. I just wrote phi as phi I plus phi I minus. Okay. This I could write as phi I plus times W xn plus 1, okay, plus is this correct what I did? If I'm asking the question, it must be wrong. So there's a term I'm missing here. And what No, it's not normal ordering. You see, I'm trying to write an equation. So I had this, right, which was phi I minus into W. I wrote this as this way. I have to add another term to make the equation true. That term is what? That term is the commutator, right? So I have to add to it the commutator of phi I minus x1 with W of x2 to xn plus 1. And this commutator makes sense because remember W is also an operator. Now it's a true equation. So I can write it as this way plus that way. Okay? Okay. This is equal to notice the first term, these two terms together are what we would have called the normal ordered product of phi I of x1 with W of x2. Okay? The first two terms are what we would have called the normal ordered product. Do you see? Because in this term, the plus is on the, if you were to expand a normal ordered product out, you'd get two terms, one where the, sorry guys, this is my innate thing. I needed to put the phi plus on the right, not the phi minus on the right. As I told you at the beginning, I always innately have a thing where I like to put this. Okay, yeah. Sorry, this should have been minus, this should have been plus. Okay, and then I need to commute. I mean, the equation we wrote earlier was also useful, except it wasn't the normal ordered product. Okay, now this is the normal ordered product. Okay? So the normal ordered product is where the minus terms appear on the left, okay, and the plus terms appear on the right. So these two terms together look like the normal ordered product. Okay? Plus we have a commutator. X1 okay, is this fine? Okay. So the first term, okay. Now what is this commutator? Okay, let's analyze the commutator. Look at the form of W. The form of W is what appears on top. What will happen when I take phi I plus and I commute it through some of these guys? Remember, what happens when I take phi I plus and I commute it through some of these guys, okay, is that I'll get the commutator of phi I plus with one of these field operators, with one of these operators which has, say, a phi I minus up there. Okay? But you see that of xm, this commutator is in fact the same as the commutator with because there's no commutator of the plus and the plus. So the commutator is only of the plus and the minus. Okay. Now, there were too many things we had to keep in the side. Notice that, remember the contraction we wrote as theta of x10 minus x20 into this commutator plus another term which had a theta of x20 minus x10 into the other commutator. But this is, remember the assumption is that, x1 is the largest time. That's the one I pulled out. So this is the contraction. In the case when x10 is larger than x20, this is the contraction, right? Because x10 is larger than xm0, because we chose x10 to be the largest time. Okay. So do you see this? Okay, good. Now see what happens when you take this phi I plus and you commute it through these W's. You will get these different commutators. Phi I plus will commute with each of the each of the phi i's that's uncontracted there. But it will convert every uncontracted phi I into a contraction. Do you see that? So this is the set of all terms where phi I x1 is uncontracted. This is the set of all terms where phi I x1 is contracted. Okay. Plus all terms there are only two possibilities. Okay, x1 can be uncontracted or x1 can be contracted. Okay, so this the sum of these two terms is just the same as this expression but with one higher n. Do you see? But this is equal to w of x1 to xn. Can you just think about this a little bit and make sure that you understand it? Yeah. What did we do? Let me just take, we are trying to prove this by assumption. So we are assuming that this theorem is true for some value of n. And then we are trying to prove it's true for n plus 1. If we can do that, then we know it must be true for all n, right? That's just mathematical induction. Now we said, say the theorem holds for some n, and let's call this right hand side, let's call this expression, let's call this w. Okay, good. Then for n plus 1, we just call the latest time, we called it x10. Then I just wrote down what the time ordered product is. Because it's time ordered product and because this is the latest time, I can just pull it to the left and write the time ordering of the other guys. By assumption, this time ordered product of n, it's now time ordered product of n fields only because it goes from x2 to xn plus 1. You see? By assumption, this is equal to the right hand side of Wick's theorem. So it's equal to this times w. This is the inductive hypothesis. Then I said, well, you could have written out phi I of x1 as the positive frequency part plus the negative frequency part. Okay. You could have then written this as the negative frequency part, you just keep as it is. The positive frequency part you move to the right at the cost of a commutator. Okay. Now, if you look at these two terms together, that looks like the normal ordered product of phi I with w. Okay. So it's as if in all these normal ordered terms, you just added one more phi I x1. So this now becomes a set of all terms that you would have got in w of x1 to xn plus 1, where phi I x1 was uncontracted. Okay. Then there's also a commutator. The commutator goes and hits, it doesn't act on these numbers. Remember, we made a big song and dance about why these were numbers. So the commutator doesn't commute with these numbers. But for instance, like if you look at the top expression and an x5 or an xn is uncontracted, okay, then it will go and it'll act on it. Okay. But because x10 is the largest time, this commutator with any such field in the product is the contraction. It is a contraction because the contraction had two terms, but by assumption here x10 is the latest time. Therefore, this commutator produces all terms where x1 is contracted. So we have the sum of all terms where x1 is uncontracted and the sum of all terms where x1 is contracted. And that is the same as all possible contractions now. Okay, and that's the right hand side of Wick's theorem for n plus 1. So that leads, that tells you that if you assume Wick's theorem for n, then you would find that you could prove Wick's theorem for n plus 1, and that tells you, and since it's true for n equal to 2, and since we have the statement for n implies a statement for n plus 1, we've proved it in general. Okay. So do you see how it works? Yeah.
Phi I minus of x1 comma phi I plus of x1, because this is the
This one. This one. No, or this one.
This is the contraction that phi I of x1 comma phi I of x1 and phi I of x2. So that will give you a commutator.
It'll give you a commutator. The commutator.
Phi I of x1 with phi I of x2, right?
Sorry, what you're asking? There's one term here which is phi plus of w. That becomes a sum of various commutators where the phi plus acts on the various terms inside w.
I'm asking that contraction of phi I of x1 and phi I of x2.
Yes.
That gives the commutator between phi I of x1 and phi I of x2.
No, of phi I plus and phi I minus. That's what we wrote earlier sometime back. In the case when x10 is larger than xm0, and another term where sorry, you mean why didn't I write plus and minus? Oh, thank you. That's what you meant. Yeah, sorry. No, I did write, no. See, this is just a contraction of x1 and xm. This is a commutator of x1 of plus and minus. Okay. The contraction of x1 and xm, if you open your notes sometime back, you will find looks like the commutator of plus and minus with x10 minus xm0 plus the commutator of minus and plus when xm0 is larger than x10. That's the formula we derived about 20 minutes ago. Because x10 is larger than xm0, there's only one term that appears, and therefore this contraction is the commutator of phi I plus and phi I minus xm. Okay. Okay.
Excuse me, sir. When you wrote down this T of phi I x1 dot dot phi I x n plus m n plus 1, and then you wrote phi I x1 into w of x2 dot dot x n plus 1, right?
Yes, go on. Yeah.
How to write that w operator in place of the
Because
all
that's
other?
the assumption. We are assuming that the theorem holds for some n. So that means that if you take this time ordered product of x2 to xn plus 1, it's in fact a time ordered product of n fields only, because it's 2 to n plus 1. So there are n fields. But we assume that the theorem is true for n, right? For some n. Therefore, you can replace, by this assumption, by the inductive hypothesis, you can replace T with W.
Okay, so you have taken that T of the whole term as W of x1, xm, right?
Which is the right hand side of Wick's theorem. Yeah.
Okay. And in the right hand side, did you write it is a normal order, the first line in the right hand side? In the very right hand side, phi I of x1. No. Just this right hand side of the lower board.
This one.
No, right hand side, sir. Equals to, you have written, no? Yes. Is it normal ordered, the first term? Phi I of x1 into w of x2 dot xn plus 1?
This one. Yeah. That's right. This is normal ordered. Yeah.
Okay, so the whole term is normal ordered, right?
No, I took the first two terms. Look, these two terms. This one and this one. Can you see?
Yes.
Those two terms are the normal ordered product of phi I with W.
Oh, okay. And now I got it. Now.
These two are the sum normal ordered product, and then there's an additional commutator, which is this term.
Right. Yeah, got it. Thank you, sir.
Fine. Okay, good. Okay. So what is the significance of Wick's theorem? Well, the significance of Wick's theorem is that it makes the evaluation of these time ordered products of elements very simple. For instance, say we were trying to evaluate only a vacuum expectation value. This is what I said here. The vacuum expectation value, for as I'll say later, in the end we'll formulate everything in terms of vacuum expectation values, right? This is the kind of matrix element we were evaluating previously, except I have put psi1 equal to psi2 equal to the vacuum. So say we were trying to evaluate this kind of a vacuum expectation value. Then this vacuum expectation value, you see, we have this Wick's theorem. Which term in Wick's theorem will contribute to the vacuum expectation value? Yeah, only the last term, right? Because no other term has a vacuum expectation value. Normal ordered products of operators never have a vacuum expectation value, right? Because in normal ordered products, we always have, creation operators to the left and annihilation operators to the right. So you'd never have a vacuum expectation value for a normal ordered product. So there is only one term which can contribute. First of all, you know that this guy, okay, if you have interaction picture operators, is just 0, by the way, if n is odd, okay, which might not have been obvious. If you just looked at this, you might have said, how do you know it's 0? Maybe time ordered product of 3 fields has a vacuum expectation value which is non-zero, but in fact it doesn't have, right, of these interaction picture fields. It doesn't have any expectation value if n is odd. It only has an expectation value if n is even, and that expectation value is the sum of all the contractions. Okay, and which was not obvious in the beginning. You might have thought maybe there is something, but you'll never get any vacuum expectation value if n is odd, You'll only get a wave if n is even, and that is just the sum of all contractions. So it's become much simpler to evaluate than what we had to do earlier. So you see, and it's also true if you have non-trivial in and out states. So Wick's theorem is very significant because it simplifies greatly the evaluation of these expectation values of these time ordered products, which is after all what we wanted to do. If you remember where we started this lecture, these kinds of expectation values are what appear in Dyson's formula, and they're what we need to evaluate to understand perturbation theory. Okay. Okay. Okay, I'm going a little slow, but let's give 15 minutes. Okay, is this good? Everything? Fine. Now let's keep this and let's evaluate. Let's complete the evaluation we had of this propagator. This you already did in the assignment, which I hope all of you have submitted. Okay. So let's continue evaluating this thing. This is what we started to evaluate, but we didn't evaluate completely, right? Now, there are various ways to evaluate this. One way is, just to compute the commutator, we wrote down various expressions for this. Here's another simple way to evaluate this. It's the vacuum expectation value of, of phi of x and phi of y. That's because, remember, by, it's the difference, the contraction is defined as the difference of the time ordered product minus the normal ordered product. Okay. If you take the vacuum expectation value, then, the normal ordered product has no vacuum expectation value. On the other hand, the contraction is a number. So its vacuum expectation value is a number itself. Therefore, the contraction can also be written as the vacuum expectation value of the time ordered product. You see this? Okay, good. Okay, so let's do this for the case of, so let's evaluate this. Okay, let's consider. Then what happens when you compute the vacuum expectation value? Well, when you compute the vacuum expectation value of this time ordered product, you only have to keep track of terms where the creation operators act on the vacuum here. Right? So when you look at this 2-point function, this 2-point function just gives you a delta of k minus p. Okay. So it cancels a 1 2 pi cubed also. So what you get looks like okay. That's what it is for the case where x0 is larger than y0. Okay. For the case where y0 okay, you can run the same game and we'll find that the answer is which is obvious because it's just the same expression with y and x interchanged. Okay. So this is what it is for y0 greater than x0. Okay. So in fact, the expression is symmetric in x and y because the full expression looks like this. So the contraction looks like Let me erase this. Looks like this into theta of y0 minus x0 plus theta of x0 minus y0 okay. The difference between these two terms is that in one case you have p dot x minus y, in the other case you have p dot y minus x. Okay, but it's the whole expression is symmetric in x and y. Each individual term is not symmetric, but the whole expression is symmetric because that term is just this term with x and y flipped. Okay? So if you do that, you get something that's symmetric. You see this? So this is the full expression for the contraction. Yeah. Okay. Now the theta function looks a little annoying, but in fact we can get rid of the theta function as you did in the assignment by writing this in a slightly different way. Okay. By writing this as just 1 second. Let me make sure my epsilon conventions are consistent. Right, plus epsilon. Yeah. I just wanted to make sure it's consistent with my sign conventions, which I mess up all the time. Okay, good. Yeah. Okay. So what does the I epsilon mean here? Okay. The I epsilon here is, so this you can check is actually the same as this. Okay. So what is the I epsilon here? The I epsilon here is a convention that tells you how to do the integral. Okay, what does it mean to say that we've put an I epsilon here? It tells you have various integrals here, and this integral has two poles. Okay. The poles sit at p squared. So imagine that this looks like p0 squared minus p squared minus m squared plus I epsilon is equal to 0. Okay. So they sit at the two square roots of this quantity. And the I epsilon tells you that when you do the integral over p0, okay, how should you move the poles off the real axis? Imagine there was no I epsilon here. Okay. Then you have this integral over p0. Okay. And the integral over p0 has two poles which sit here. One sits here at minus omega p, and the other pole sits here at plus omega p. Okay. And this integral is ill-defined because you're integrating through a pole, which is a problem. Okay. Okay. So the I epsilon tells you that you shift the poles a little bit, okay, off the axis so that you can then do the integral. Okay. So the I epsilon basically tells you is that the poles now move to p0 squared is equal to omega p squared minus I epsilon. Okay. So they move to p0 is equal to omega p minus I epsilon for omega and minus omega p plus I epsilon. So let me just say something here. You know, when you take the square root, okay, if you take the square root of this, and you will find that the square root actually has an I epsilon by omega p. Okay? But when we write an I epsilon, we only care about the sign of the epsilon. Okay, so this is the same as writing. You know, if I were to, you know, evaluate the square root, I would find some factor of omega p here, but that is the same as an I epsilon. Okay? So I epsilon into 2 is the same as I epsilon. Okay? I epsilon into 3 or I epsilon into 10 or I epsilon into any. Huh? What?
We are modifying the epsilon.
Yeah, we are modifying the epsilon, but the I epsilon really is meant as an integral prescription. Okay, the numerical value of the epsilon doesn't mean anything. Okay? So that's why the poles, one pole moves a little below, and the other pole moves a little above. Okay? So instead of the pole sitting here, one pole goes here, and this pole goes here. Okay? So this tells you how to do the integral. Now the poles are not on the axis, okay? And it tells you, okay. So now let's check that this expression with this pole prescription gives you back this. That's what we want to check. Okay, good. Maybe I'll erase Wick's theorem. Fine.
When we do contour integral,
Yeah.
just deform the contours around the poles and do the integration.
Well, you have to see how you deform the contour. Okay. So the epsilon is giving you a rule for how you deform the contour. It's telling you that, huh?
Like keeping the contour same and moving the.
It doesn't matter. Oh man, what did I do? Yeah. So you can move the poles here, right? Or you can leave the poles where they are and do this. Okay, it doesn't matter. It's completely equivalent. Okay. Okay, let's check. How will we check since this got? Okay, let's do the integral and then later we'll see if we get the same expression. You guys have it in your notes. You see, I said that the poles did this, right? So one pole has moved here. This is the pole here, and this is the pole here. Okay. So the P0 poles are here. Okay? And the expression I'm claiming looks like, minus IP into x dot y into p square m square plus I epsilon. Okay, good. Now say x0 is larger than y0. Okay. Then we look at e to the minus IP into x minus. So look at the zeroth term. Okay? So this looks like x0 minus y0, okay, plus minus I p dot x. Okay. That's the term that we have there. Okay. Now this term, because x0 is larger than y0, this is some positive term. So this term, it makes sense to take the contour and complete it through the lower half plane. Okay. So when you compute the contour through the lower half plane, you pick up the contribution from this pole. Okay. So the residue at the pole looks like 1 by P0 minus omega P, P0 plus omega P. Okay, that's P0, that's P square minus M squared. Okay. There's an I epsilon here also, but we don't care about the I epsilon right now. We're looking at the residue at this pole. Okay. So the residue just looks like this term. Okay. So we pick up 2 pi I into 1 by twice omega P. Okay. And then we pick up the remaining term, minus I P dot x minus y, except that this P here is now just a P where you've put the omega P to be on shell, okay, where the omega P has become positive. Okay. In the case when x0 is smaller than y0, to the lower half plane, Now what happens? Sorry, so the upper half plane. Okay. Now what happens? Now you pick up the other pole, right? Okay. So now we pick up the pole at P0 is equal to minus omega P. Okay. Now when you pick up the pole at P0 equal to minus omega P, okay, the residue looks like, so there are various minus signs you have to be careful of. Okay. So yeah. So you pick up, you go this way. Okay. So now we are going counterclockwise. Actually, we should have picked up a minus sign here. Sorry, when we are going clockwise here, and I think I forgot to put on top an I here. Okay, I'll put an I in a second. One second. Let's just do this. So the residue is 2 pi I, okay, into minus 1 by twice omega P, okay, because you pick that up. What should I write here? Should I still write e to the minus I P dot x minus y? Should I write the same expression or should I write something different? I already integrated, but should I? But when we wrote this expression, what did we mean? When we wrote
is
this,
it I into P y0 minus x0 because x0 is less than y0 here?
Yeah, that's correct. But you see, when we wrote this expression, when we write this, right? So actually, let's write this as d3. This is actually what the residue is. There's an integral. Okay. When we write this expression, what do we mean when we write this expression, right? So the 2 pi will cancel, it will become a 2 pi cube. Okay. And in fact, the minus I and the I will also cancel. So you'll get, there should be an I there, which I'll put in a minute. Okay. And everything else will cancel. Okay. When we write this expression, what do we mean? The integral is only over d3p, but this looks like a 4 vector. Right? When we write this expression, we mean you take p equal to this with a positive sign. Okay. But here, what is happening to p is that we are picking it up with a negative sign. Okay. So we should, now you might have thought that, the sign of p gets reversed, but remember omega p is the same as omega of minus p. Okay? So the residue you can write as plus I p dot x minus y d3p by 2 pi. There was a 2 pi to the 4th, all these factors just cancel, so you get 2 pi cubed. Okay. So you see that the full answer looks like this in the case when theta is into x0 minus y0, into this in the case when y0 is larger than x0, okay, which is what we had earlier. Let me just put a factor of I. Okay, which matches what we had earlier. I don't know, I shouldn't have put this. Yeah, so it looks like e to the I p dot x minus y into theta of y0 minus x0 plus e to the I into p of y minus x, which I've written as minus I p dot x minus y in the case when x0 is larger than y0. Okay, I should have put a factor of I here. I forgot to do. Yeah. Okay, so you see that this pole prescription that we have, you can, we could have written the contraction in this way with these different theta functions. Conversely, you can write it as a 4 integral, except with this pole prescription as a d4p integral, but with this, with an I epsilon pole prescription. Yeah. Yeah.
Last time when you did this commutation,
yes.
Said that for space like it will be 0 because I can rotate it and take it to minus r.
What will be 0?
Space like separation, the commutation will be 0.
The commutator is 0 for space like separation. Yes, but where? Yes, okay.
From here, how can you for space like from here? How can you? This is a Green's function expression, right?
Sorry, one second. What is the relation of this to the commutator?
No, this you can relate because
I didn't understand. Sorry, what is the question? I didn't understand. This is the time ordered product. This is not the commutator. This is the time ordered product.
the Green's function can be related to the commutator, right?
There are different kinds of Green's functions.
Feynman Green's.
The Feynman Green's function is not the commutator. Okay, the commutator is the retarded Green's function. Okay, so that's not the Feynman Green's function. This is called the Feynman Green's function. For us, it's just a time ordered product, and it's this. It is not directly related to the commutator. Yes.
This is the general expression for Green's function.
No, what? No, no. What do you mean by general expression for Green's? It is the expression for a particular.
Yes,
Green's function can mean different things. It's the expression for the time ordered product.
that is the general. If I put plus I epsilon both sides, if I go up by plus I epsilon, then that becomes retarded or advanced.
Yes, there are various ways of doing things. That's right. You can get retardant and advanced by putting a plus I epsilon P0 minus P0, and you can also put delta functions. Yeah, there are various other epsilon prescriptions which will give you, yes. Okay, so
My question is, from that commutation, can you show that if x minus y is space-like separate or x square minus y square is space-like, this is zero exactly?
yeah, we showed it in the beginning. Remember when we checked causality?
That way you showed by rotation, right? Because it's a connected component, space-like component can be rotated to minus r.
So it's this. What is the difference in these computations?
Here,
This is not, first of all, the commutator. This is not the commutator. This is the time ordered product. So from here, we cannot show what happens to the commutator. You would have to evaluate the commutator, but we did evaluate the commutator using this, and we checked, but that is not a different computation, it's the same computation. What's different about that? This expression, I've evaluated the time ordered product, right? Which is this. There's a different expression which you get if you evaluate the commutator. The commutator will have, which we did evaluate, and we found it was zero. So what is the question? You want to check whether the commutator can be written with an I epsilon prescription. That's a different question, but that it can be written with an I epsilon prescription.
It's written that.
Well, okay, but right now we've not written the commutator with an I epsilon prescription. You can write it. What you want to check is if you take the commutator, which we computed, how would you write the commutator with an I epsilon prescription?
And show that it's zero for.
No, that's a trivial thing, because once you write it with an I epsilon prescription and you check it's the commutator, it will be obvious. There are no different calculations here, right? Everything is the same calculation. Whether you write the time ordered product this way, the I epsilon prescription is meant to ensure that you get the right answer for the time ordered product. Similarly, whatever I epsilon prescription you use for the commutator will have to be designed so that you get the right expression for the commutator. This is the right expression you started with. You started with the definition. Then we said, well, we could have written it with an I epsilon prescription. For the commutator, you will start with the calculation that we did, and then you will see, can I find an I epsilon prescription that will make the commutator work? Okay. If you can, good. If you can't, then it doesn't work. Okay. So you will have to check, can I find an I epsilon prescription? If you find an I epsilon prescription by construction, it will match this. Okay. We can check next time what the I epsilon prescription for different Green's functions is. But you see, there's nothing deep happening here. This is the correct expression for the time ordered product. Similarly, for the commutator, there is a correct expression which you already evaluated. You could look at other products as well. Then you can ask, can I find an I epsilon prescription to get the same expression of 4-vector notation? The 4-vector and the 3-vector are not different. They're just, you do the P0 integral, you get back to the 3-vector. It better work. Right? So there is nothing.
Time ordered commutator not, sorry, time ordered product not for.
The time ordered product is not the commutator. There are different kinds of Green's functions. You should be clear about that, right? This is a particular product. This is the vacuum expectation value. In fact, it's a contraction that we evaluated. So the vacuum expectation value of the time ordered product is one particular term. You could also look at the commutator. There's something else. You could also look at the vacuum expectation value of just the product of fields. That's called the Weinberg function. Okay? So that also, there's some I epsilon prescription for that as well. So every different kinds of product you can look at. First, you look at what this answer is in this form. This is the correct answer. Then you see, can you write it as an I epsilon prescription as a 4 integral? And you often can. Okay. So that's maybe next time when we look at the I epsilon more, we'll see how to make it work. Okay. But it's a triviality to go from here to here is just one step. And then if you've shown this vanishes for space like that will also have to vanish. Okay, did I answer the question? I mean, maybe what I haven't done is I haven't told you what the epsilon prescription is explicitly. Let's do that next time. But whatever it is, it has to work. It's not a different calculation. It's the same calculation.
Excuse me, sir.
Yeah.
Is it possible to explain that how do you get the residue in that form? Actually, I didn't understand that.
In which form?
In that 1 by 2 omega p e to the power that part.
Well, there was a 2 pi I from the residue theorem. There was an I which I'd forgotten to write here, but I now wrote. So there was a 2 pi I that came from there that cancelled with this. The 1 by twice omega p just came from the 1 by x square minus a squared. So I think it is 1 by x minus a x plus a and factoring out one part. So remember, it's p0 minus, actually that expression is half erased on top. It's p0 minus omega p and p0 plus omega p. When you pick up the residue at omega p, you get the other term, which is p0 plus omega p, but p0 is omega p, so the residue is 1 by twice omega p. Do you see that?
Right, yes.
In the other case, you get minus 1 by twice omega p. You have to be careful about the signs. Go clockwise and anti-clockwise.
Okay.
Okay. Okay, sounds good. So let's stop here.